on the same side. This is more stable because this hydrogen is smaller. I'm just auditing. Because they're looking to hire up to break the law. Plus, I'm taking organic-II. Well, I would say Halogen 20. Put it in the camera.
All right, so let's go ahead and pick up with Chapter 8 here. Chapter 8, we're going to look at this entire full set of alkene reactions. Now, I gave you guys one of these. It's actually attached as the last page in this handout. What you're supposed to do with this handout is work it. And we're going to go over this, I guess Monday or something like that, whatever. We're going to work all these problems. If you don't have your other thing with you, you can just look at the last page as these sets of reactions as we work our way through them. Now, we were just talking about carbocations and the fact that resonance-stabilized carbocations are good. I said that anything next to the carbocation that has an unshared pair of electrons was going to stabilize it. If we have an oxygen next to the carbocation center, one of these electron pairs can move in, and we get the oxocarbocation. Oxocarbocation or oxocarbonium ions are relatively stable species. I actually had the pleasure of measuring the lifetime of one of these guys in aqueous solution. As some work that I did years ago, it's about 10 to the minus 9 seconds. So when we talk about something being stable, it's still pretty unstable, but 10 to the minus 9 seconds is fairly long-lived by maybe a factor of 1,000 for most carbocations. The chlorine we saw in the previous example, this goes in to form a chlorinium ion, and the most stable in the bunch is if you have a nitrogen. Nitrogen would form this ammonium ion. Now, we've all heard of ammonium ions, haven't we? Ammonium ions are very common. Ammonium, NH4, very stable species. So we have a very stable carbocation here. This exists mostly as the ammonium ion, but with positive character here. This exists mostly as the oxonium ion with carbocation character here. Chloronium ion, again, positive character next to it. So these are stable things. The other example we looked at was the benzyl carbocation. Now, I said the benzyl carbocation was resonance stabilized, and these are 4 resonance forms showing that. We start off with the positive charge in our benzyl position. Step 1, we move electron pair in to give a double bond. But when we do, we're taking electrons away from this carbon, so this is now positive. We can remedy that by moving in this adjacent pair, like this, to give us a double bond again. A positive charge is now down here. Doing it a third time, positive charge is here. In the resonance hybrid, the positive charge is spread between this, and this carbon. So we spread it out over the ring. One of the rules in nature is if you take a charge and you spread it out, it's going to be more stable. This is why drawing resonance forms is useful. And we will use this, resonance forms like this, to rationalize lots and lots of organic reactivity. Any questions? So benzyl, anything with electrons next to it, those are examples of stable carbocations. Tertiary, secondary, primary, methyl. We know the ordering goes this way. What would you think about this guy? Where do you suppose he would rank? Well, if we simply count carbons, it's a tertiary carbon, isn't it? But look at the bottom six-membered ring here. This is a cyclohexane boat, isn't it? It's a boat where we've taken these two carbons and we've tied them together with another carbon. Now remember what the end of a boat looks like? The end of the boat sticks out, doesn't it? Sticks up. So what we have is this carbocation. Now remember, carbocations are sp squared, and they must be planar. If we put our positive charge out here on the end of our boat, it is not planar, and it is in fact very, very unstable. So what you need to remember, benzyl, anything with electrons next to it. Then you go to tertiary, secondary, primary methyl, and things like this that cannot be planar are very, very unstable. Yeah?
How do you know that something can't be planar? Like,
Well, look at it. Okay, I mean, in this perspective, you can see this is a regular boat, right? Except we've tied these two ends together. They can't go flat. We've
Okay.
tied it down.
So what you're saying is only things that can be planar can be categorized in those things. Is that correct?
All right, this is our first set of simple reactions. During this chapter, during this phase of your life, you will develop the skill of looking at a reaction like this. Alkene plus HX. You will say to yourself, this is going to have Markovnikov regiochemistry. Regiochemistry describes the region of the molecule where things will go. Okay? So Markovnikov regiochemistry means we're going to add our nucleophile to the most stable carbocation. HBr, we'll see if we do this in the presence of peroxide, that by gosh, we get the opposite result. And we'll call this anti-Markovnikov. If we add halogen, X2, chlorine, bromine, iodine, we will get a 1,2-dihalide. And the stereochemistry will be trans. If we add HOX, where X is a halogen, we will get a Halohydrin. We will learn that Markovnikov regiochemistry is observed for the hydroxyl group. When When we do hydration, we're going to form a carbocation intermediate and convert an alkene to an alcohol. This type of reaction, we get lots of rearrangements. And finally, we can do a more civilized version of that reaction using mercuric acetate, followed by reductive workup as a second step to get a Markovnikov alcohol. Now this might seem a little overwhelming, but it just makes good common sense. Our next set, hydroboration-oxidation. We're going to get an anti-Markovnikov alcohol.
How do you know that's anti-Markovnikov?
Well, in this you can't, but what you will train yourself is if you see BH3THF followed by peroxide, you will say to yourself, anti-Markovnikov alcohol.
Can you explain again what anti-Markovnikov is?
Anti-Markovnikov, the nucleophile, that is here, the hydroxyl group, would add to the carbon next to the carbon that we give the most stable carbocation. We'll see how this happens later. But it's the opposite result. Osmium tetroxide permanganate, we're going to form cis-1,2-diols. We're going to do carbene reactions where we form cyclopropane additions to our double bond. Finally, we're going to wind up the chapter talking about oxidation. If we add peroxide, we can get epoxides. Ozonolysis, we're going to split the double bonds. Same thing with permanganate, split, break down to CO2, whatever. Again, we're going to try to do these in a simple, logical fashion. So, let's get started.
So with KOH, follow what that last slide you said. Copper and ether.
That was an oxidation. Well, we'll do that later. That's one of the last things we'll talk about. All right, we just spent time looking at this reaction. We take an alkene, we take HBr. Everyone in this room now knows we are going to form an intermediate carbocation that will be on the secondary carbon, and we will get this halide. Everyone knows that. However, if we do this reaction in the presence of a peroxide, we get this as our product. This is what we get from the ionic addition. If we simply throw in peroxide, we get this. This is referred to as anti-Markovnikov regiochemistry. Our most stable carbocation would be here, right? Instead, we're going to add our bromine here. Now, what in the world could peroxide be doing?
I've got a question though. Doesn't the carbon already have 4 bonds, so how are you adding the extra bromine to that carbon that's already got? It's a
No, this
CH3.
has 3 bonds. 1, 2.
Yeah, but there's an H that attaches to the CH3, doesn't it become a CH3?
No, this is a CH. Now it's a CH2. It's all there.
Also, you just switch the H around.
All right. This is a peroxide. I put R groups because we're talking about an organic peroxide. So these could be anything. Benzyl, benzoyl, whatever. Everyone has probably had experience of some sort with Clarisil, etc. That's benzoyl peroxide. So we have benzoyl groups. We'll learn what those are next semester. But the functional thing is we have this oxygen-oxygen single bond. What peroxides do is split this bond homolytically to give 2 free radicals. Now the free radicals you get from benzoyl peroxide attack bacteria, they kill them, your face clears up, you're beautiful. Okay? In this reaction, the peroxide is going to react with HBr, and we're somehow going to get a different product. All right, here's our peroxide. We're going to split it in half. Once we get the peroxy radical, what can it do? Remember, anything with an unshared pair of electrons, with an unshared electron, is very reactive. And it's going to look for something to abstract an electron from. What's going to happen is this is going to react with HBr. And it's going to pluck hydrogen with its electron from HBr. When this happens, we get an alcohol and a bromine radical. Now remember the chlorination reaction we saw a bit ago. We had a chlorine radical, right? So these things can exist, they do exist. Bromine radicals even more stable, actually. This is the thing that's going to add to our alkene. Okay? In the ionic addition, we added the proton. Here, we're going to add Br radical. Now, our bromine radical is going to add to this. And what do you think it's going to form? The most stable radical. It's going to add to our double bond in such a way that it gives the most stable radical. Just like the proton added to give the most stable carbocation. So we could get 2 radicals here, a primary or a secondary. Just like the secondary carbocation is more stable, the secondary radical is more stable. Everything that you just learned about how to stabilize a carbocation works for radicals. So this reaction makes great sense, actually. Instead of forming the most stable carbocation, we're simply forming the most stable radical. Now, what's this radical going to do? Well, it's unhappy. It doesn't have enough electrons. It's going to react with another mole of HBr, pluck off a hydrogen, and generate the bromine radical all over again. And then this will do another cycle and another cycle and another cycle and whatever. Bottom line here, addition will always occur to form the most stable radical. That will then take a hydrogen atom from HBr to form what turns out to be the anti-Markovnikov halide. Yeah.
Okay, so how do you know when it's going to be anti-Markovnikov and when it's going to be
If you're doing an ionic addition with HBr without peroxide, that's Markovnikov.
Okay, so
If
this one
you
doesn't
throw in
have,
peroxide,
oh, this one does have peroxide.
if you throw in peroxide, it's anti.
How do you know this one has peroxide?
It says, if we go back here somewhere,
Oh, but if you just saw that,
this is what you would see on the exam.
right, okay. But for that, if you go forward a few slides, the last slide we were just on. No, I mean this slide right here. The one this right here.
I'm coming.
That one. Doesn't say there's
This doesn't say
peroxide.
because.
Right, so when it be Markovnikov, so it's going secondary be more stable than primary, so the BR would attach to this secondary carbon.
Except that we have a bromine radical shown. Anytime you see a radical, you're gonna know that you're doing a peroxide reaction.
So anytime you see a bromine with just one
One electron,
electron,
right?
it's a radical. And you know,
This is what you would see. Oops. Oh wait, let's talk about why radicals follow carbocations very quickly, then we'll see some real problems. These are visualizations of spin density. Remember, electrons have spin. So one of the things we can calculate is where the radical is in a given radical species. If we have a methyl right here, the methyl is essentially planar, and we'll have radical density top and bottom. If we did this on a tertiary carbon and calculated where the radical character is, where this extra electron is, okay? Turns out that it's not just on the central carbon, but actually spends some of its time on all these other places. It's also not planar anymore, it's slightly puckered. This is a much more stable situation than this because we spread the radical character out over lots of atoms. So that's the rationalization. Now what you would see on an exam would look like this. That's how you would know you were doing a reaction in the presence of peroxide. So for each of these, draw the most stable radical. And then add the hydrogen to give me the anti-Markovnikov alkyl bromide. Now remember, when you draw the radical, it's going to have a bromine attached, right? Because Br dot is the thing it's going to add. Primary carbon, tertiary carbon. The most stable radical would be on the tertiary carbon, wouldn't it? Which means that bromine must add to this carbon. Now our bromine's already on there. This is going to pick up hydrogen from HBr, and that is our product. The most stable radical is at the tertiary center. Remember, Br dot adds here, leaving the radical here.
So where does that extra electron move to?
Where this electron,
Yeah.
it pulls off H dot off of HBr. That gives us another Br dot, and the whole thing starts over again.
Sorry, that was it. The first step was adding the bromine.
Right. First step is
Which
to
causes
add
the radical
bromine
to occur.
radicals, Br dot. Bromine radical adds to this carbon, leaving the radical here. This then pulls off H dot from HBr to reform Br dot. And then it goes again and again and again.
So there will always be a radical.
Yep.
So unlike with the Markovnikov situation, the H doesn't add, it's just the radical from dot adds instead of H. That stops.
Our next one here. We could form a radical on our secondary carbon or on the carbon next to the chlorine. If we were doing carbocations, where would the carbocation go?
Next to
We did this, it'd go next to the chlorine, of course it would. So if we're going to add Br dot It's going to add here to leave the radical here.
Doesn't matter where you stop.
No. Now this is going to pick up hydrogen radical from HBr, and we're left with the 1,2 halide. Yeah.
So on a test, your final product would be without the radical?
Yep. Remember, on an exam, I probably will ask you to draw the radical intermediate, and then the final product.
And so the H picks up the extra electron, or the radical dot.
The radical, this radical
Yeah.
picks up H dot from HBr.
So that H goes next to the C element, but it's not the
Right.
right special
Hydrogen goes right here.
Now, if the double bond was on the side where it would be, where the Sp2 and the chlorine is,
So it
then the
would be
bromine would attach to the chlorine.
What, it would be here?
It like on the side where it's like the.
Here?
Yeah, that's where
That's
the
the
double
same
bond
compound though. It'll be the same compound. If we have the double bond down here somewhere at the bottom, then it would be a messy reaction, you'd get it on either side.
is. But we had that one problem where the bromine
That was
attached to the.
ionic though. Remember? Because that would form the most stable carbocation. Here it forms the most stable radical. Our next one, we could form a primary or a secondary radical. Br dot is going to add here to form the secondary radical here.
Sorry, why did it add on to the CH3?
Why did it add on? Br dot, going to add here to give a secondary radical. Secondary radical would be more stable than the primary. Always add to form the most stable intermediate. Radical or carbocation. Most stable. This picks up hydrogen. And finally, this is our friend benzyl, isn't it? Most stable carbocation would be at the benzyl position. Most stable radical is at the benzyl position. Therefore, Br dot will add to give this as a radical. This will then pick up a hydrogen from HBr, this carbon, to give this product. If you want to think about it in Markovnikov terms, Markovnikov would look at, let's just do this one. Markovnikov would look at this and say, 2 hydrogens, 1 hydrogen, right? So the bromine should add here. This should get the hydrogen. That's Markovnikov's rule. The anti-Markovnikov rule is backwards. The carbon that has the most hydrogens gets the bromine. I always think, though, it's better to do it in terms of intermediates. All right, next. If we take an alkene and react it with a halogen, so we're talking here bromine, chlorine, or iodine, what we get is a 1,2 dihalide. That means they're next to each other. If we have stereochemistry in our ring or in our compound, the bromines, chlorines, iodine, whatever, are always trans to each other. Now what's happening here is a 2-step reaction involving an intermediate. We know this pi cloud has lots of electrons, doesn't it? It has electrons. What it's going to do is these electrons are going to attack, in this case, bromine, Br2. When they do, we'll split off Br minus, and here we have our bromine sitting on top of our pi system. Just imagine our pi cloud, and our bromine is sitting there. It's just as happy as it can be. Bromine is split, if you will, into Br plus and Br minus. And the Br plus, just like we said H plus, is sitting on the pi system. This is what we call the bromonium ion intermediate. Now the second step here is going to be this Br minus attacking this. Remember I said that we always get trans addition. The reason we get trans addition is that, remember how big bromine is? It's big, isn't it? If we go and color this in, this is what our molecule would look like. Big honkin' bromine up top. In order for Br minus to attack, and it's even bigger, it's got to somehow reach one of these carbons. Coming in from the top here, there's no way in the world it's going to get there. No way. The only pathway, the pathway of least resistance, remember rule number 2. The pathway of least resistance is for this to come up from the bottom. When it comes up from the bottom, its little ring opens, and we get trans stereochemistry. So what you have to remember here is we form a bromonium ion intermediate. We then get backside attack of Br minus to give the trans product. Let's go back 50 years. Here comes Br2, splits. Here's our bromonium ion. It's big. Step 2, the Br minus comes in from the bottom, and we get the 1,2 dibromide. Again, the reason this is trans is that this is really big. And the only possible way for it to get to this carbon is to come in from the bottom. So what you have to remember, like I said, bromonium ion intermediate, 1,2 dihalide, trans stereochemistry.
Why does there need to be an intermediate step though?
Why does it have to be an intermediate? Was that the question? Well,
Why can't it just?
in order to explain the stereochemistry, the bromonium ion intermediate is the simplest way to explain that. In fact, this intermediate has not ever been isolated, but one with an iodine has been isolated, crystal structure done. It's a real compound. So it's known that these things do exist. All right, so this is what it would look like on the exam. Take these, please, and draw the products of our simple addition reaction. We look at this on our paper and we see alkene, Br2. I'm going to form a 1,2-dibromide. That means that each of the alkenes will have a bromine. If there is stereochemistry, they will be trans. This is cyclohexene. Now I've drawn this using a chair because we all love chairs by now. We know that this is going to add and form a 1,2-dibromide, right? When it forms this 1,2-dibromide, we're going to have a bromine on each carbon. Initially, we would form this intermediate. But everybody in this room now looks at this and says, oh my goodness, these two bromines are axial. We can't have that. And so everybody would instinctively write it with them both equatorial. Initially, it must form axial. It instantly rearranges or undergoes ring flip from axial to equatorial.
Could you show that axial again? Oh,
Must go in with the two bromines directly opposite to each other. That means they must be axial. But we know we can't have axial bromines. Oh my goodness. And so everybody, of course, would draw them equatorial. On an exam, I might draw, or might have a problem like this, and say, draw the initially formed 1,2-dibromide, and then the product in its most stable conformation. Here, we're simply adding bromine across a cyclopentene. We know that the bromines must be on opposite sides. Something like that would work. Any questions?
Does on the cyclopentane, does bromine have to be facing that way or can it be facing that way? Does it matter? That is the story.
Sorry.
On the cyclopentane?
No, they could be reversed.
Okay.
I know we
like
made
the
two
bromine
chiral
can be facing
centers
left
there.
or right, or doesn't matter?
Doesn't matter, we made
It's
two
not-
chiral centers.
Okay.
You know, another good exam question would be, do this addition and then tell me the stereochemistry at each center. That would be a big question, wouldn't it?
Right, and then it can face anyway, right? Doesn't matter.
Hmm?
The stereochemistry doesn't matter,
No.
like you just said. So when does the stereochemistry matter? When it's
Let's see,
Sure.
this would be S stereochemistry. And this one would be R. Now you could have done that. All right, closely related is the addition of HOBr or HOCl to an alkene. Very closely related. Why is it closely related? Well, here, instead of having Br, we simply have OH and Br. This reaction also gives trans stereochemistry. Okay? This reaction also involves an intermediate. Intermediate is the same one we saw with the addition of bromine. This is the bromonium ion intermediate. The one thing you have to remember in this reaction, you're going to add bromine to one carbon, OH to the other. And when we were adding bromine to both, it didn't matter where we put them, did it? What you want to do is look at your starting alkene and say which carbon would give us the most stable carbocation. Same question over and over and over again, right? Which one would give the most stable carbocation? Well, the secondary would. That is where the OH group goes. We say that this is Markovnikov relative to the hydroxyl group. So let's see the whole mechanism. Oh, before we do that, typically you won't write HOBr, although I will, because it makes it so much clearer. What you'll often see in the book and everywhere else is N-bromosuccinimide, water DMSO mixture. This is N-bromosuccinimide. This really is just a source of Br+. We'll actually use this in lab to do a reaction very similar to this. On your exam, you will see HOBr probably. 99% sure. All right, here's what's happening. When we did the addition of bromine, our ring attacked, we formed a bromonium ion intermediate, right? The bromonium ion intermediate was attacked by Br-. Here, we're simply letting water, or OH, be our nucleophile instead of Br-. Wind up with this unstable intermediate, loses the proton quickly, and we get this. Let's look at the movie. Here's our alkene. Going to form our bromonium ion intermediate. Doesn't matter where it comes from. Water is now going to be our nucleophile. This is going to lose that proton, and we get our trans addition product. HOBr, what you say to yourself is, I'm going to form an addition product with bromine on one carbon, OH on the other. OH is going to go to the carbon that will give the most stable carbocation, and they will be trans. Why do we have Markovnikov relative to hydroxide? Well, if you really look at the bromonium ion intermediate here, molecules will adjust their electron density to make themselves the most stable. If they're willing to give up electrons, they will. Our primary carbon can give up fewer electrons than our secondary carbon. Secondary carbon can pull them in from the methyl group, donate them to this, and stabilize it. That means that this carbon has a bit more positive charge than this one. OH attacks the more positive carbon to give a product. Molecules are very generous that way. They will distribute their electrons to make the whole thing more stable. All right, so this is what it looks like on the exam. Step one, you look and you say, I'm adding HOBr or HOCl. You're going to put hydroxyl group on one carbon, bromine on another. The hydroxyl group will go to the carbon that would give the most stable carbocation. In our first one, we have a secondary and a tertiary. Where does the OH group go? On the tertiary. Most stable carbocation is here. hydroxyl group adds to that carbon.
Doesn't matter which way you're facing the hydroxyl.
Nope, nope, nope,
As long as it's transit to both, right?
nope, just a drawing. Remember, you can orient your drawing any way you want. Here we have a primary carbon. Here we have a tertiary carbon. Most stable carbocation is going to be here. Therefore, the hydroxyl group will add to that carbon. The product, this will be an OH. Chlorine will be bonded here. Doesn't matter which one you draw, axial. The chloromethyl is actually slightly bigger than the hydroxyl group, and that's why I did it this way. Our next one, we have a secondary carbon and a tertiary. Most stable carbocation will be on the tertiary. Therefore, that is where the hydroxyl group will go. Bromine will go down here. But remember, they must be trans to each other. Hydroxyl group, the carbon that gives the most stable carbocation, trans stereochemistry. Any questions? These things that we've been doing are typically called, except for the HBr reaction, HBr peroxide, that are called ionic addition reactions because we have an ionic intermediate. This next one is the king of ionic addition intermediates. It is the brutal acid-catalyzed hydration of an alkene. It's a brutal reaction. We are going to do nothing more than make a carbocation at the most stable center and then add water. The thing that makes this reaction so brutal is that the carbocation very, very often will rearrange itself. If we form a carbocation that's not quite stable enough, the molecule will rearrange itself to make a more stable one. But let's see how this happens. We're going to add our proton first. It's going to add, here we have a secondary carbon, here we have a tertiary. We're going to add the proton to give the most stable carbocation. Once we have that, hydroxyl group will add to the carbocation. Here's our alkene. This is going to pick up a proton to give the most stable carbocation. Primary center, secondary center, tertiary center. Proton adds here. This is our most stable carbocation. Once we have that, water or hydroxide will simply add, lose a proton, and this is our product. We'll do a reaction very similar to this in lab in just a little bit. Our movie. Again, this is our same alkene here. Step one, we're going to protonate to give the most stable carbocation. Now this is planar, remember. Water could attack from either top or bottom. Coming in from the top, that's this intermediate, have to lose a proton, and we wind up with our alcohol. Any questions? Simple, brutal OH group to the most stable carbocation center. Go ahead and do them. You look at your alkene, you ask yourself, which of the alkene carbons will give the most stable carbocation? We have a primary and we have a tertiary. Carbocation will go here. That means OH will attach to this center. There's our stable carbocation. There is our final product. Carbocation, tertiary center, final product. Yeah.
So at that carbocation, originally a water molecule goes there, and then something
Yeah.
plucks up.
Yeah,
plucks
water
up the
will
hydrogen off
attack
the
when we
water
just lose
molecule.
the proton. That's all fast though. That happens about 10 to the 9th per second.
So what comes and takes the hydrogen off the water molecule?
What does? Another water.
Okay.
All right, here, primary carbon, tertiary carbon. Our carbocation will be at the tertiary center. That means that we will add the OH group to that carbocation, and it will look like this. Doesn't matter which one you put axial. Carbocation, final product.
Real quick, where does the, so you break the double bond right there, where does it get the second, first hydrogen to become CH3, so it becomes that methyl?
This hydrogen adds here, doesn't it?
Okay, and that breaks the
That makes it
double
a
bond.
CH3. All right, this next one is a real problem, isn't it? This is like an oh my goodness. They're both secondary, aren't they? We could add to either one of them. In fact, however, you only get one product in this reaction. If we add here, so we just add a proton down here, that gives us this secondary carbocation. Now remember how I said molecules were so nicely cooperative? Well, this guy looks at this and says, well, wait a minute. I'm a tertiary center. This is a secondary center. We would all be so much better off, so much more stable if the carbocation was here. So what this does is it rearranges. in a rearrangement. We're going to grab this pair of electrons and the hydrogen and simply let it slide from here to here. What we have done, hydrogen with its electrons, called a hydride, simply slides over from here to here. When it does, it leaves the positive charge here. This is called a 1,2 hydride transfer. We'll talk a whole lot more about these in the future. Again, hydride, hydrogen with its electron pair, this whole thing simply slides from here to here. Oops, wrong button.
Why the methyl?
Methyl stays, just the
It
H
moved from the top
minus
to the side though.
slides down.
Why did the methyl move from the top to the side?
Oh, I just turned the molecule, that's all. When I drew it, doesn't matter. Yeah,
Maybe some question, but why did the oxygen go?
I'm sorry?
The oxygen?
Well, we haven't added the oxygen yet. We're just playing with the carbocation. Initially, we're going to form this one. Hydride is going to slide down to leave the tertiary carbocation, and that's what picks up the hydroxyl group.
So if you were to draw the alcohol and the methyl on
Doesn't matter which side you draw, top or bottom. Now, we're going to talk more about rearrangements later on. What I want you to simply realize is that whenever we have a carbocation intermediate, whenever we have a carbocation intermediate, we can get this type of rearrangement. Probably on the second hour exam, I will not put rearrangements, but we'll talk about them again more. So let's make sure that we understand that these things can happen. Okay?
The exam, do you want us to do those steps like?
I could probably ask you to draw the carbocation and the final product. Yeah. Now, I described the hydration as brutal. There's also a civilized way to do it. Civilized way is to use mercuric acetate, step 1. And step 2, react that with sodium borohydride. When we get to carbonyl compounds, we'll call something like sodium borohydride a reducing agent. It donates an H minus. This reaction is going to involve the formation of a mercury bound to our alkene. The mechanism. If this was a bromine, that would look familiar to you, wouldn't it? Wouldn't it? That would be our bromonium ion. All that's happening here is mercury is functioning as a Lewis acid accepting electrons, and we're forming a mercurinium ion. Now, just like when we did the addition of HOBr, our next step is going to be attack of hydroxide. Where do you think hydroxide is going to attack? It's going to attack at the carbon that would form the most stable carbocation, just like it did with HOBr. So we have a secondary carbon and a tertiary. Hydroxide is going to attack the tertiary. This looks a whole lot like the addition of HOBr, doesn't it? Except that we're left with this mercury dangling down there. How do we get rid of the mercury? Well, that's step 2. Sodium borohydride, boom. Mercury's gone. We're left with a Markovnikov alcohol. No chance for rearrangement. No carbocation. Beautiful, clean, simple reaction. Only problem is you flush a lot of mercury down into Lake Michigan. But, you know, shoot, we send that down Mississippi anyway. Any questions? So on the exam, if you see mercuric acetate followed by sodium borohydride, all you do is you say to yourself, civilized reaction to give an alcohol. One of the really fun things to do in organic chemistry is called synthesis. And on the exam, we will have a little bit of synthesis. Synthesis is fun because you get to think backwards. A synthesis problem might be, tell me how to make this molecule. What alkene would you need? And what reaction conditions would you use? All right. Well, we could all do this, right? Right? We look at this and say, what kind of a molecule is it? That's an alcohol. How many ways do you know to make alcohols? 2. That's it, just 2. One is acid-catalyzed hydration, and the other is reaction with mercuric acetate. Both of these give Markovnikov alcohols. The difference is mercuric acetate does not have the opportunity for rearrangement. Why is that important here? Well, because we're going to add out here, aren't we? What's this? That's benzyl. That's the most stable carbocation in this molecule. Right? So if we do an ionic addition, this thing is going to rearrange itself 7 times if it has to get the positive charge here. So you would look at this and say, gee, I need to do mercuric acetate. We could not make this with acid-catalyzed hydration because we would get the benzyl carbocation and the OH group would go here. Oh, doesn't go on the ring, not until next semester.
But following Markovnikov's rule, you want the most stable carbon.
Right, that's not the ring. The ring itself is incredibly stable.
Right, so with that, drawn as an OH.
Yep. Nope. In fact, doing chemistry on a benzene ring is a science all to itself. Next semester. All right, so what we want to do is use mercuric acetate. If we look at the starting material that we have suggested, we have a secondary carbon and a tertiary. We know that mercuric acetate is going to give us Markovnikov regiochemistry, so we're going to put the OH group here. Initially, our mercury is going to be bonded here. Our second step, which you would have to put down on the exam, sodium borohydride to get rid of the mercury. Now we're going to do lots and lots of synthesis in this course. Next semester we're going to do a ton of synthesis. It's so much fun. This is just an example of synthetic logic, how you would choose your reaction conditions in order to get the product that you want. Yeah,
So the mercury would go on the carbon.
on this alkene carbon is where the mercury goes, OH goes here. All right, we've done our first set. Let's start on our next set. Now, we're not going to go through the whole thing. I'm just trying to see how far we do go. Now we'll go through a lot. In this set, we're going to look at reduction. In reduction, we're going to take an alkene and convert it to an alkane. We're going to look at osmium tetroxide, potassium permanganate to give 1,2 diols that are cis to each other. After those, we'll break, we'll finish up the others on Monday, and on Monday, we'll go through this set. Okay? So work these at home, and then Monday, we'll go over them all. Oh, I guess we did start with hydroboration-oxidation, sorry. All right, hydroboration-oxidation. Like I said, we know 2 ways to make alcohols, right? Unfortunately, both of those are Markovnikov alcohols. What if you wanted to make this guy, where the OH was bonded adjacent to the most stable carbocation? This would be an anti-Markovnikov alcohol. So there is a very simple reaction that we can do to give an anti-Markovnikov alcohol. And this reaction involves BH3. THF is simply a solvent. Tetrahydrofuran, it's an ether. Second step, we're going to dump in peroxide in the presence of base. Bottom line here, when you look at your alkene and you do hydroboration oxidation, the hydroxyl group will wind up on the anti-Markovnikov carbon. That's what you need to remember. Now, just like the reaction with mercury that we just saw, we're going to wind up with an intermediate with boron attached to our ring. Our second step is just designed to get rid of the boron. Okay, step 1. We're going to take the boron-hydrogen bond, and in one beautiful fell swoop, one concerted reaction. Concerted means everything happens at once. The hydrogen with its electrons will go up. Electrons from the pi system will go down, and we make our boron intermediate. Call it borate intermediate, not boring. This reaction is concerted, this bond breaks, this one makes at the same time. Now, why does this thing orient this way and not the other way? There are actually 2 reasons. Remember, This is a tertiary center, that's a secondary. This will accommodate a positive charge better. So it will be slightly more positive. Probably the greatest impact, though, is that this boron, with all its stuff attached, is big. And so it's going to go to the carbon that's the smallest. So here we have a methyl group, little tiny hydrogen, prefers this just based on size, and the fact that this is tertiary means it accommodates positive charge better. So it lines up like this, both of these bonds happen at the same time, and we get this intermediate. You'll note, because both of these go on at the same time, the boron and the hydrogen must be on the same side, right? As we make both bonds at the same time, they have to be next to each other. Our second step, we're just going to get rid of our boron, convert the boron to an OH group with peroxide. Now your book has a mechanism for exactly how this happens. We're not going to talk about that. It's not going to be on the exam. If you want to know more details about how you convert the boron to the OH, please look it up. Now, as always, there's a movie for that. Again, we're going to take, I used a different alkene here. We're going to take this alkene, these two add at the same time. They must be cis to each other. Convert the boron to the OH group. There it goes. All right, here it comes. Both of these are transferred at the same time. And boom, this is our borane intermediate. In our second step, we do peroxide. They wind up on the same side. This is called syn, not just cis, but syn, S-Y-N. If they were opposite, we would call it anti. We all know that cis and trans don't always work anymore. Oh, so we can describe this as a syn addition. Oops, let's go back and see if we can make it run again. Maybe not. What I want to stress is how the addition is truly conservative. The H3 is going to come in, transfer this and this at the same time, and that's why they must be adjacent to each other, and simply convert this to the OH. Any questions? So we have three ways to make alcohols now. Two Markovnikov, one anti-Markovnikov. Go ahead and draw the products for these guys. Remember, the hydrogen and the OH group must be on the same side of the molecule. And the OH will be bonded to the carbon adjacent to the most stable carbocation. We look at our two here, secondary, tertiary. This would be the most stable carbocation, so the OH winds up here. OH and the hydrogen must be cis.
From the Academic Success Center.
Oh.
May I speak to your class for a few minutes?
Sure, let's finish this one. All right, here we have a simple alkene reacting with BH3THF. We look at our alkene carbons. We have a secondary and a tertiary. This is going to be anti-Markovnikov. So the OH is going to be bonded to the secondary carbon. Hydrogen's going to go on here. They're going to be cis stereochemistry, but again, because we have a single bond, we don't have to show that. Anti-Markovnikov alcohol, cis or syn addition. Any questions?
Bring your ID. Science, computers, and math is walk-in. English and accounting is by appointment. Did you have any questions for me? Yes.
What if you don't have a student ID? I don't have a student ID.
Get your student ID, because then you get a lot of benefits with it. And you can, Academic Success Center, you can use a computer lab, plus you get $10 free worth of printing.
So,
Get your student ID. Did you have any other questions? Thank you, and we
Sure.
return to your regularly scheduled program.
All right, the last one we're going to do today, catalytic hydrogenation of alkenes. All we're going to do here is take an alkene and convert it to an alkane. That actually always seems like a waste because alkenes do so much nice chemistry and alkanes don't. But if you take an alkane in the presence of hydrogen gas and platinum, what happens is we add hydrogen to our double bond, and the addition of hydrogen is from the same face. So it's either cis addition, you could call it, or more properly, syn addition. Very, very simple reaction. Only thing you have to remember, hydrogens go in on the same side. When we say hydrogen in the presence of platinum, this is usually, platinum is expensive, you may know that. The way you do this is you take a teeny, teeny, tiny amount of platinum, because it's a catalyst, and you put it on charcoal. So you have this big bucket of something is 99.9% charcoal. Take a scoop, dump it in, bubble in hydrogen gas, and it works. Then you just filter off the charcoal and you're left with your stuff. Nice, very simple reaction. The way this thing works, this is your platinum surface. When hydrogen gas encounters a platinum surface, it binds to the surface. It actually binds to the platinum atoms, and in doing so, the hydrogen, H2, splits into two hydrogen atoms. Now they're bonded to the surface like this. Step 2, the alkene with its pi system comes and it sits down on the platinum surface. Platinum surface likes electrons. So this comes and it just sits down. Now these two discover each other, sitting next to each other. And all in the world that happens, hydrogens move on the same face over to here, and they wind up bonded next to each other. Properly said, the hydrogen is adsorbed, with a D, adsorbed to the surface. The alkene adsorbs to the surface as well. The two hydrogens slide over, simultaneously from the same face to give cis addition. Trivial reaction. Quickly draw the products of these catalytic reductions. These are so very simple. All you're going to do is convert your double bond to a single bond. The only thing you have to remember is that the two hydrogens you add coming from the same side. So that will affect the stereochemistry. Up here it makes no difference. We're just going to add one hydrogen to each carbon. And there's our alkane. Now this next one is going to make a difference, isn't it? We're going to add a hydrogen to each carbon, but because it's a ring, it's going to have stereochemistry. Now this could actually form two different products. One where hydrogen is added to the top here, another one where it comes in from the bottom. This is a case where size matters. And if you look at this molecule, on the bottom half we have a 2-carbon bridge. On the top half we have a 1-carbon bridge. That's just slightly smaller. Therefore, this space is going to bond easier to the platinum, and we'll get this as our product. Then we'll get some of the other two, but this will be the major product.
You have to throw out the hydrogen atoms.
Well, you know, I would, if this was an exam, I would. You know why? Because I wanted to make sure that whoever grades my exam knows damn well that I know this is cis addition. Communication, very important. And the last one the same way. We're going to add hydrogen to our 2 carbons here. They're going to come in from the same side, and we're going to have a cis dimethyl cyclopentene. Any questions? Okay, today's Wednesday, right? That means we have lab again tomorrow. Lab, I believe, is column chromatography. Before there was such a thing as TLC, there was column chromatography. After you have done column chromatography, you will be so grateful that TLC exists. Column chromatography can be a real bother. I will put a video up on the website, on Blackboard, and it will show the technique for pouring the column. This is the most important part, pouring the column. What you have is a slurry of silicon dioxide. Pour it continuously into this little column. Have to make sure as it goes in there are no air bubbles, no breaks. You don't do anything stupid to it, so you wind up with a perfect stack of this stuff. Then you run your compounds down there. We're going to take spinach, and we're going to separate the chlorophyll from spinach.